Let's talk about effective stresses in soil. So as described in the previous discussion, soils are multi-phase systems. So in a given volume of soil, the solid particles are distributed randomly with void spaces between. So the void spaces are continuous and or occupied by water and or air. So to analyze the problems, such as compressibility of soils, bearing capacity of foundations, stability of embankments, and lateral pressure on earth retaining structures, we need to know the nature of the distribution of stress along a given cross-section of the soil profile. So we can begin with the analysis by considering a saturated soil with no seepage. The figure here shows a column of saturated soil mass with no seepage of water in any direction. So the total stress at the elevation of point A, which is here, can be obtained from the saturated unit weight of the soil and the unit weight of the water above it. So basically that means that at this point A, the stress being experienced in this area is caused by the soil above it and the water above it, and the stress or the pressure caused by that weight can be obtained through the use of their unit weights respectively and multiplying that to their respective heights as well. So stress at A basically is equal to first the pressure due to or the stress due to this water here, which is can be obtained by multiplying the total the h here, which is the height of the water, times the gamma water or the unit weight of water, plus this height from this point below the water and then to the point A. So this height is just basically equal to HA minus H times the saturated unit weight of this water, of this soil right above our A. So the total stress in here at the elevation of point A, no, is denoted by this symbol. Gamma water is the unit weight of water. The gamma sat in here is the saturated unit weight of the soil, and capital letter H is the height of water table from the top of the soil column, and H sub A is the distance between point A and the water table. So the total stress given by the previous equation can be divided into two parts. No, a portion is carried by the water in the continuous void spaces. So this portion acts with equal intensity in all directions. So the rest of the total stress is carried by the soil solids at their points of contact. So the sum of the vertical components of the forces developed at the points of contact of each solid particles per unit cross-sectional area of the soil mass is called the effective stress. So this can be seen now by drawing a wavy line A to A through point A that passes only through the points of contact of the solid particles. So let P1, P2, P3, and P4 or P sub n be the forces that act at the points of contact for the solid particles. So the sum of the vertical components of all such forces over the unit cross-sectional area is equal to the effective stress or force over the area. So again, if as is the cross-sectional area occupied by solid-to-solid contacts, then the space occupied by water equals to the total area minus the area no, denoted in small letter A. So we can write now the stress at point A is equal to this equation, and where U in here is actually the pore water pressure, or that can be computed through the multiplication of the unit weight of water times the height of the saturated soil right above our A. Yes, our U in here is also referred to as the neutral stress or the pore water pressure, which is um, denoted by small letter u. So therefore, our effective stress, which is denoted by this symbol with a prime, beside it is equal to the height of the soil column times the, so therefore the effective stress, no, or this symbol with the prime is equal to the height of the soil column right above A, and the gamma prime, which is equal to our gamma saturated minus the gamma water. So we have here a sample problem, no? We have here a soil profile is shown in figure 9.3. So 9.3 is here. Calculate the total stress, the pore water pressure or the neutral stress, and the effective stresses at points A, B, and C. We are given with the value of our gamma dry, which is equal to 16.5 kilonewton per cubic meter, and the location of our groundwater table, which is 6 meters below, no, point A. And we have also the gamma sat, which is equal to 19.25 kilonewton per cubic meter, and then the height equal to 13 meters. So therefore, at point A, the total stress is basically, when you talk about these stresses, no, the total stresses, the pore water pressure, and the effective stresses are just basically the stresses that are caused by the things or by the weight above our specific point, no, being considered for. Therefore, at point A, no, there's nothing above it, so the total stress is zero. That is, the H in here is actually zero, man said, no? So that's why the pore water pressure and the effective stresses are equal to zero. So now at point B, so what are the things that are above our point B, no? So this layer, no, equal to 6 meters in height, which has a unit weight dry equal to 16.5. So our total stress in here is just basically equal to the pore water pressure and the effective stress. So total stress is equal to gamma dry sand times 6, no? That is equal to 99 kilonewton per cubic meter. Per square meter rather, because it is stress. Our pore water pressure is zero because the height of the water above this layer is actually zero, meaning our water table starts here. So basically in this area there is no water. So we have no h to multiply to our, or our h that we can multiply to our gamma water to come up with a pore water pressure is zero. So that makes our pore water pressure equal to zero. So our total, or our effective stress, which is equal to the total stress minus the pore water pressure. So 99 minus 0 is equal to 99 kilonewton per square meter. So at point C, no, so we have to remember that effective stress is just equal to the total stress minus the pore water pressure. So at point C, so we are going to consider the heights of the layers above it. So first we have, for the total stress, we have this one, that is gamma dry times this H, which is 6, no? That is 6 times 16.5 plus this one, the stress or the pressure that is caused by this one, which is basically equal to the unit weight of this layer times its height. Now that is 13 times 19.25. So our total stress at point C is equal to the stress caused by this layer equal to 6 meters plus the stress caused by this layer. So that is 349.25 kilonewton per square meters. Our pore water pressure at point C, or our neutral stress at point C, is just basically equal to the height of the water table above it times the unit weight of water. So that is, this is 13, and then we multiply that with the unit weight of our water in terms of kilonewton per cubic meter, that is 9.81. We would come up with our pore water pressure equal to 127.53 kilonewton per square meter. And therefore, our effective stress at point C, which is equal to the total stress minus the pore water pressure, that is 349.25 minus 127.53, is equal to 221.72 kilonewton per square meter. So let us explore more on the varying situations or concepts of effective stress. So first, so in this first situation, no, we are asked to solve for the effective stress at point A if the situation of our soil layer, our soil profile is like this one, no, where our ground surface is located in this area, and then our groundwater table is below the ground surface, the ground, yes, the ground surface. So if we are to, if the unit weight saturated is not given, no, in the problem, then we can just solve it through this equation, which will require us to have the value of our specific gravity and our void ratio, no. So siguro in a problem, if the gamma sat is not given, it could be that the given is specific gravity and the void ratio, so that enables us to solve for our gamma sat, no, because in this illustration it has been specified that this layer here with height h2 it has a saturated unit weight, and the layer which has a height equal to h1 has a dry unit weight. So you also have what we call the submerged unit weight, which is what we use, no, this is actually what we use on the computation of our effective stress at point A, no. So it could also be that the effective stress can be obtained through subtracting, no, the pore water pressure from the total stress, or we could also use the submerged unit weight, no, what we call the submerged unit weight, because in some cases also you might be asked for the submerged unit weight. So that is basically just the gamma saturated of that layer minus the gamma water, no. So it is basically just this one. So if you are going to be asked for the submerged unit weight, no, in a problem, automatically you would have to think of that is equal to the gamma sat minus gamma water. So you have to bear this in mind. So you no longer have to derive the equation from this one down to that one. So you just have to memorize this equation right here. So it would be just easier for you. So the total stress at point A is equal to the things that are above our point A. So basically this one and this one, no. So first, therefore, the total stress at point A is equal to H1 times gamma dry, no, that is the pressure due to this layer, plus gamma sat times H2, no, and then that is the pressure caused by these layers. If you're going to add up them, those two, you will come up with the total stress that is being experienced by our point A. So our pore water pressure at A, since our groundwater table in here is located H2 above our point A, so basically our pore water pressure in here is just the height of the groundwater table from our point of consideration times the unit weight of water. So basically that is just H2 times the unit weight of water. So our effective stress can still be calculated through subtracting our pore water pressure from our total stress, or we can directly solve that through this equation, no, gamma dry of H1 plus submerged unit weight is equal to the gamma sat minus gamma water times the H2, no. So you can use this one, you can directly use this one or subtract this one and this one, or use this equation. It's up to you. So the second situation is this one, no. Our groundwater is on top of our soil layer, no. So there is a water above our soil layer. Okay, so the saturated unit weight is just the same as well as the submerged unit weight. So the total stress at A is basically everything that is above is everything above A. So that is gamma water, because this is pure water, mano. It has been specified here. So this H1 is just the height of the water, no, and the stress that is caused by this layer is just equal to the gamma water times the H1, no, plus the gamma saturated times H2, no. So that is how we compute for each of the stresses that is caused by this layer. So we add them two, and then we would come up with the total stress at point A. So our pore water pressure, because water is above here, no? So it covers H1 and H2. So basically that is saying all throughout this layer, it has water, no? Or water is present from H1 or top of H1 until our point A. So basically that makes our pore water pressure equal to the unit weight of water times H1 plus H2. That is the total height of our water present in this soil profile, no? Because dito pimingon nga nalang diri ang water, no? Kaya gi-indicate sa problem nga naa daw diri. So basically, from here to here na ay water. So that's why for us to compute for the pore water pressure, we have to use the whole depth equal to H1 plus H2. So our effective stress is just basically total stress minus pore water pressure, no? So this concept does not really change all throughout the concept or the discussion of effective stress. This will always be equal to total stress minus pore water pressure. So this equation here is this one, total stress, and this equation is the pore water pressure at A. So simplifying this equation, we can use the formula for our effective stress at point A if the situation is given like this, no? And that would be equal to our submerged unit weight times H2, no? So our submerged unit weight is equal to the gamma saturated minus gamma water. So we can simply use this equation, no, whenever we are presented with this kind of soil profile. So but still I would recommend you to still use this equation, no, because there might be a little confusion or difficulty for you to memorize each of the formula for these different situations. So another one um, situation for our soil profile when we are asked to solve for the effective stress, no, of point A, still point A. So the saturated unit weight is just the same. The submerged unit weight also does not change. It is still equal to the gamma saturated minus the gamma water. So our total stress at A is equal to gamma sat times H1 plus H2. So you might have wondered why are we using gamma saturated for both the two layers, whereas or even though the illustration here actually specifies gamma dry. However, our ground surface here lies together or on the top of our soil here. So basically, our ground surface and our groundwater table are coinciding in this situation. So even though the problem or the profile or the given is the gamma dry, we're thinking that we have water above it, meaning this layer, which has a thickness equal to H1, is not actually dry, no? Kaya naman siya, naman daw diri ang water table. So all throughout the section of this one, it has actually water in it, meaning it is not dry. So sometimes in some other problems, we are also required to really analyze the soil profile, no? So the total stress at point A is basically the stress due to the layer with H2 and the layer with H1. So we are going to use the gamma sat because the situation presents that our groundwater table is actually on the ground surface. So our pore water pressure is still equal to H1 plus H2 times the gamma water because our um, groundwater table is H1 plus H2 far from our point A. So effective stress is still equal to total stress minus pore water pressure, and we have this formula, this equation rather, is from this one, and this is actually from our pore water pressure. So simplifying that one, we come up with the equation of our effective stress at point A if the situation is presented like this. So now let us also talk about the effective stress in the zone of capillary rise. So I know we are very much familiar with capillary rise, no, with our subject in hydraulics. So we have here the height, no, or the capillary rise in millimeters, which is or which can be solved through this equation, which contains C. C is actually a constant that varies from 10 to 50 millimeters. So D sub 10 in here is the effective size in millimeters, and E is the void ratio. So the pore water pressure at a point in a layer of partially saturated caused by capillary action would now become U is equal to the negative. S is the degree of saturation in percent over 100, which is constant, times the gamma water, and H in here is the capillary rise in meters. So katong equation kagani in the previous slide is actually the capillary rise in millimeters. In some cases, you would really have to convert that to have consistent units. So basically, if the problem actually presents us with the presence of capillary rise in the soil profile, so we have to adapt this, or you have to add or incorporate this equation to the solution of our determination for the effective stress at a point of consideration. So we have here a problem, no? So it is indicated here that there is a zone of capillary rise. So let us proceed to the solution, no? Okay, we are asked first to solve for the effective stress at right above A. That is, so that is equal to the stresses of the layers or the weight right above A. So basically, that is just this gamma dry times 4 meters, no? Kay mura man ang naa sa ibabaw sa atong point A. So that is 16 times 4. That is equal to 64 kPa. So wala siya poor water pressure. Kay ang groundwater table is napa siya diri sa point B. So basically, diri walay water. And then, that would make the H for our pore water pressure determination equal to 0. So therefore, the effective stress and the total stress at point A is just equal, no? There is no pore water pressure. So right below A rather, no, we have here. So right below A, and then that is before B. So kaning that is actually what we refer to in this situation as zone of capillary rise. So that is 4 times 16 minus negative 9.81 times 60 times 1.2 over 100. So this is actually the formula that we have discussed in the previous slide, no? So basically, for you to determine or for you to include in the computation or in the consideration the zone of capillary rise, you have to subtract it, no, from this one, from the layer right above it, no? So that is 4 times 16, that is that is actually, that refers to this layer here, minus the zone of capillary rise, no? Sa mo ni siyang equation. So actually mahimo mo ni siyang plus, no, kay negative times the negative here, ma-add siya. So that becomes the effective stress right below A is equal to 71.06 kPa. So it's still, no, bigger than the effective stress at A, because we know that stress or the pressure actually is proportionate to the depth. So as our depth increases, the effective stress also increases, despite the subtraction here that we had. So next, we are asked to solve for the effective stress at point B. So that is equal to the stress that are stresses that are caused by everything that lies above our point B. So that is 16 times 4. That is the stress caused by this layer, plus the stress that is caused by this layer, which is equal to H, 1.2 times the unit weight for this layer equal to 17. So that is equal to 84.4 kPa, no? This is the effective stress at point B. So still, there is no presence of pore water pressure in this layer or at this point, because the groundwater table is still below our point B. So the effective stress at point B and the total stress at point B is just equal because the pore water pressure is 0. So now for effective stress at C, that is equal to all the stresses that are caused by everything that lies above C. First, we have this layer, which is equal to 16 times 4. So we have here this layer 1.2 times 17, which is the gamma given for this layer, plus 18 minus 9.81 times 6. So plus 18 minus 9.81 times 6. So the pore water pressure in here is actually this one, no? 9.81 times 6. And the stress caused by the layer, no, equal to the height of 6 meters is actually 18 times 6 also. So, mara lang siyang factor out ang height or depth nga 6 and then nag-come up siya aning equation in total. So, calculating that one, we have the effective stress at C equal to 133.54 kPa, which is still equal to the total stress minus the pore water pressure, no, at point C. So, nanay pore water pressure sa C because our groundwater table lies above our point C already. So we also have effective stress of saturated soil with upward seepage. So in this situation, no, we have an upward seepage due to the inflow, no, through this inlet in here up to our soil. So meaning water will seep to our soil profile, no, in an upward direction. So if we are going to consider point A, total stress at point A is equal to gamma water times H1. The pore water pressure at A is equal to the gamma water times H1, no? And then the effective stress is just equal to total stress minus pore water. The effective stress equal to 0 because at above point A, all that lies above it is just water, man. So at point B, no, this one, the total stress at point B is equal to H1 times gamma water plus D, no, which is the height from point A to point B. That is D times the gamma saturated. And then the effective stress at point B is just equal to the total stress minus pore water pressure. So that is basically this one minus this one. And then if we are going to simplify the equation, we would come up with this equation. So at point C, no, at point our point C is here. Point C is here. So the total stress at point C is equal to H1 times gamma water plus H2 times gamma saturated. So pore water pressure at point C is equal to H1 plus H2 plus H here. No? Muna siya ang nadugang plus H here. Sometimes this is already given in our problem. So H basically is the height of the rise of the water column if you are going to insert a piezometer at point C, no? So that is the rise of the water. That is the pressure head basically times the gamma water, no? So that is the pore water pressure at point point C rather. And then the effective stress at C is just still equal to the total stress minus the pore water pressure, no? So if you're going to simplify the equation from this one subtracted by this one, then we will come up with this equation, no? So also in the problem, we are asked to solve for the seepage force per unit volume that is equal to H divided by H2 times gamma water, no? So therefore our F is equal to the hydraulic conductivity, no, hydraulic gradient rather, hydraulic gradient times the gamma water, no? H is the head loss, which is the height of the piezometer if we are going to insert, no, it into our soil profile. And H is the length of our soil. So another scenario is that if there is a downward seepage in our soil. So meaning, ang flow sa atong tubig is from gikan sa babaw and then magawas dayon siya, no? At the bottom of our soil. There is an outflow, no? In the bottom of our soil. So kaganiha, gikan sa ubos, no, pasaka man to siya. So kani gikan sa babaw, no? Gikan from this source, our water rather will seep through our soil in downward direction, no? So total stress at point A is just equal to H1 times gamma water. Pore water pressure is equal to H1, no? And it times gamma water. So effective stress is just the total stress minus pore water pressure that makes it 0. So the total stress at point B is equal to everything that lies above it. That is H1 times gamma water plus D times the gamma saturated. So the pore water pressure is just equal to H1, kaya naman na diri atong water, no? Atong groundwater table, atong water table na, atong water table. So that is H1 times H1 plus D minus H1. So that is actually the pressure head at point B, no? Times the gamma water. So effective stress at B is still equal to the total stress at minus the pore water pressure at point B. So if we're going to simplify, no, the equation, that this is the total stress minus the pore water pressure. So if we're going to simplify that, we'll come up with this equation. So the total stress at point C is here. So that is going to be equal to H1 times the gamma water plus H2 times the gamma saturated for this layer. The pore water pressure at C is equal to H1 plus H2 minus H here, or that is the pressure head if we're going to insert a piezometer at point C, times the gamma water. So still, at point C, the effective stress is equal to total stress minus pore water pressures. If you're going to simplify now the equation which contains the total stress minus our pore water pressure, we will come up with this equation. So still, if we are going to solve for the seepage force per unit volume of our soil profile here, the formula is just the same, no? Please refer to this. So if our soil has no seepage, so it is just similar, no, to what we have discussed before, the soil with upward and downward seepage. So the same lang siya. Wala na siya yung mga H diri, no, because there is no seepage. So we have here a sample problem, no. This is our soil profile. So we are asked to solve for the total stress at point A and the value of H if the effective stress at A is equal to 81.6, and you also ask for the effective stress at B. So first solution, let us solve for the total stress at A. So basically that is equal to everything that lies above A, that is 5 times the unit weight for this layer, which is equal to 20.11, plus 5, which is the height of this layer, times the unit weight for this layer, that is 19.03. So that would be equal to 195.70. So that is our total stress at point A. So now for problem number 2 or question number 2, we are asked to solve for the H here. If our effective stress is 81.6, so bali siya, no, H ang ipangita diri, katong i-times nato dito sa gamma water para makuha ang pore water pressure. So ang given diri is ang effective stress at A. So effective stress at A is equal to the total stress, which is 195.70, which we have previously solved, minus the pore water pressure, which is equal to 9.81, that is gamma water, times H, no? So kanidere, H ang ipangita. So you just have to equate this equation, no, with the given value for our effective stress, and then we'll come up with the value of our H. So bisan pag ina ning itsura, no, sige na ning itsura, H ra gyapon na siya for the computation of our pore water pressure. And then the effective stress at B, this one. So that is 81.6, which is the effective stress at A, times the given for actually for the compressible silty clay, ang given niya is Y bar na, no, or gamma bar, which is equal na siya to gamma saturated minus gamma water, no, katanggi previously discussed nato na. So kani siya diretso na lang nimo ni siya og multiply sa kaning height niya. Kung given ka og gamma bar or gamma prime rather, sorry, dili siya gamma bar, that is gamma prime. So kung tagaan kag value sa gamma prime such as this one, diretso ra nimo na siya multiply sa kani, no, plus the effective stress at this point. So that is equal to 321 kPa. So next problem, we have a soil profile with an upward seepage. So in the problem, dili siya sa illustration di ka makaingon nga na siya upward seepage unless you know the flow of the water. So since in the illustration, we have here the inflow of the water, and then therefore the water will seep through our soil profile in an upward direction. So we have here to solve for the effective stress of a saturated soil with an upward seepage. So first, we are given with the instruction, no? Consider the upward flow of water through a layer of sand in a tank as shown in this figure. So for the sand, the following are given. So we are given with the void ratio and specific gravity, no? So automatically, if we are given with this one, we are asked, we will still have to solve for our gamma sat, no, using this equation. So first, we are asked to solve for the H1 here. So that is basically the pressure head at point A. So basically for the value of our H1, we are just going to have a ratio proportional for our H1, which is from the piezometer inserted at point A. So yung height there is H1 is to 1.2, and then 1.5, no, which is from the piezometer inserted at point B, and then 1.5 is to the depth of the soil in here, which is equal to 1.2 plus 1. No? So from that, we have the value of our H1, which is equal to 0.8181. So second, we are asked to solve for the effective stress at point A. First, we have to solve for our gamma saturated because it is not given in the problem. Since we are given the value of our specific gravity and void ratio, so you can just solve for the value of our gamma saturated, which is equal to 20.27. So now, solving for the total stress at point A, that is everything that lies above A. So that is 9.81 times 0.7, which is from this layer, plus 20.27 times 1.2 for this layer right above A and then below our water table. So the total stress at point A is equal to 31.19 kPa, and the pore water pressure at A, which is equal to 1.2 plus 0.7 times 0.181, which is the height, no, of the pressure head from the piezometer inserted at point A, times the unit weight of water. So our pore water pressure at A is equal to 26.66 kPa. So therefore, our effective stress at point A is equal to the total stress minus the pore pressure at A, that is 31.19 minus 26.66 equal to 4.53 kPa effective stress at our point A. So second, we are asked to solve for the effective stress at point B. First, no, inanig siya ang flow per minute. No? First, we have to solve for the total stress and then pour water pressure at B. And then subtracting these two will bring you to the value of your effective stress. For at point B, we have 9.81 times 0.7 plus 2.2, no, that is the height of this layer, times the gamma saturated, which is this one. So that is 51.46 kPa. So for the pore water pressure, that is 0.7, no, ang atong water table kay namin na siya diri. That is 0.7 plus 1.2 plus 1 plus 1.5, no, which is the height of the water, or the height, yes, the height of the water rise in our piezometer inserted at B, times the 9.81 gamma water, no. So that brings us the value of our pore pressure at B, which is equal to 43.16 kPa. So subtracting that from our total stress at B, we will come up with the effective stress at B equal to 8.3 kPa. So the last one, we are asked to solve for the upward seepage force per unit volume, no? So the upward seepage is just basically equal to I times gamma water, no? As we have previously discussed or shown in our previous slides, no? So we just have to solve for the hydraulic gate gradient, that is 1.5 divided over the height of our, or the length of our soil. This is, or the height or the length of our flow, no? So mo ni siya. That is equal to 1.2 plus 1. Kaya diri man mo flow atong water, di ba? So that is just basically this is the length of the flow, and then the rise of the water, no, which we can obtain from the piezometer inserted in on it, equal to 1.5. So our hydraulic gradient, this is just the rise over run, no. The rise is h in the piezometer, and the run, no, imo ni siyang balihon, imo ni siyang h, mo na siya ang gidaganan sa atong seepage flow. So, the hydraulic gradient is equal to 0.682. If you multiply that to our gamma water, then you will come up with our upward seepage force per unit volume, no? Gi-specify mo niya din per unit volume of soil. So, that is 6.69 kilonewton per cubic meter. So, that would be all for the effective stresses in soil.